Come back to the Advanced Algorithms course I3341. We are continuing now with the sixth dynamic programming classical example, which is traveling sales problem. So this problem is known as traveling sales problem, and it can be described as follow. Given n cities, we have n cities, and the distances between these cities, the pairwise distances, which are given in a matrix, for example, this of size n times n, of course. The question is to compute the minimum cost of making a Hamiltonian tour. What is a Hamiltonian tour? It supposes you to start from any city and go through all the other cities, the n minus 1, exactly once. You visit every city one time and then return to the starting city S. So you make a tour visiting all the cities and at each city only one tour. This is a Hamiltonian tour. For example, let's take this example. We take the 4 cities, and how many ways can we visit these 4 cities? It is factorial 4. Factorial 4, we can have 24 different tours of these cities. For example, A, B, C, D is one tour, A, B, D, C is one tour, B, C, D, A is one tour, and back to B. Of course, always we will have to go back to the first place. And each tour will cost us differently according to the edges we are going to use in order to go from one city to the other. One way is this particular tour, A to B, then to C, then to D, and then back to A, which will cost us 97, and this is the minimum cost that we can make using this graph. To note that we can have many tours that lead to minimal cost. It is here that this is a distance matrix. Along the diagonal, the costs are 0, of course. To go from city A to city A, you are already in city A, so the costs are 0. And it is symmetric. It is a symmetric matrix if the graph is undirected. One brute force solution to answer this problem is to try all the possible tours that we can make, which is instead of n factorial, you can make it n minus 1 factorial if you suppose that you know that this is a closed circuit after all, and it doesn't matter which city you are going to begin with, there are symmetry in the circuit. So you can fix the first city. You take a first city from your choice, for example, always A, and then you will still have n minus 1 factorial ways to visit all the n minus 1 cities. So this is only an effective solution because this is a factorial. Recall the table of solutions. Let's go to see it. It's the last one in this presentation. The rule of sum, when it is a factorial, it can go only to n less than 11, less or equal than 11. So let us go back to our slide, and this is because factorial 11 is 40 million already, and factorial 12 will be bigger than 100 million. So this is effective for the number of cities is where the number of cities is 12 or less. The first thing we can think of is to see whether there is overlapping, because if there is overlapping in the solution counting, in the solution enumeration, maybe we can make the complexity less by using the dynamic programming. And the overlapping here is, as you can guess, obvious, because suppose for more or 3 cities, let's take the example of n equal 26 cities, where we are using labeling the cities in using all the alphabets from A to Z. And you are reaching a general case where, for example, you have visited in order A, then B, then C, then D, and you still have n minus 4 other cities to visit, and you don't know which order gives you the minimal cost. It overlaps with the case when you have already visited in order A, then C, then B, then D, because the same cities are remaining to be visited. You will be back to the same starting one, and you are currently at the same city. So you are currently visiting the city D. You will be left to visit the cities from E to Z, and you have to go back to A. So these two cases, these two different states, have share more than one overlapping state. So the overlapping here is very obvious. Overlapping is obvious, and we will think of dynamic programming. How to formulate the state? In addition to the current city we are visiting and from which we want to know how to minimize the cost of the Hamiltonian tour to continue, we need another parameter, which is the visited cities. We need an indicator which are the cities that are already visited and which are that are to visit yet. So it will be, for example, a parameter pause and and the subset of the visited cities. So this is the state. How to represent this subset? Do we know an efficient way to represent a set? Yes, we know. It is a bit mask. If the number of city permits, we know that we can represent the subset of visited cities using a binary integer of length n. Take an example. Suppose we have this bit mask, which is the value 18 in decimal, which is 10010 in binary representation. It indicates that the cities 1 and 4 are in the set. We can use this bit mask to represent that the cities 0 is not in the set, because at index 0 the value of the bit is 0, at index 1 the value of the bit is 1, 2 0, 3 0, and the fourth is 1. So 1 and 4 are in the set. And we can use this set to see this is the set of visited cities or this is the set of unvisited cities, which is our choice to how we will use the mask. But we can, the idea here is that we can use a bit mask representation to represent a set. This is a very efficient way. For example, to check whether a bit is on or off, you can make an AND with a left shift of the same number of bits, and to set a bit, you can make an OR with the left shift of this number of bits. You can visit visualgo.net, which is a website to support this textbook, and you can practice all bit operations over bit masks. Now let's suppose that we are going to use the bit mask to indicate the cities that are not visited yet. So we will put 1 indicating that these cities, for example here, the city 1 and the city 4 are not visited yet and we have to visit them. So what would be the recurrence relation in this case? The base case will be when you are querying a mask 0. When you have a mask 0 in addition to the position, if you reach a mask 0, this means that there are no more cities to visit, and in this case you will return what? You will return the distance from this current city back to the first one, to the starting point. So you will return the distance from pos to 0, and this is a base case. For a general case, suppose you are in a general case, you will have to compute all the possible TSP, traveling salesman problem, going from V using the new mask, adding to it the distance from this current position to V, and this for every V, for every city not visited yet. So you will take all the cities that are not visited yet, and you say, what if I continue now my way from this city V? If I continue my way from this city V, then I will have to calculate the distance from the current position to V, and then in a recursive way, I will add TSP from V and marking the new mask, which will mark the not yet visited cities, recursive calls to TSP, and every time I choose one not yet visited city, I call the recursive call over it, and of course I will pass the adequate mask. Because I chose a city V, I have to remove it from the mask to indicate that it is being visited. Now you cannot visit it again. So this is the formula: minimum of distance from pos to V plus TSP from V with a new mask, and this is for every available city not visited yet. And every available city not visited yet, we will be extracting these cities from the current bit mask, from the current mask. So what is the overall time complexity? The overall time complexity is of the order of 2 to the power n times n to the power 2. Why? Because how many distinct states we have? We have, the state is of 2 parameters. The first is the current city and the second is the mask. The mask, how many value can take? It can take up to 2 to the power n values. How many cities we can have? We have up to n cities. So the distinct states number is n times 2 to the power n. And each city, the worst case of solving each case, because we have for every V available city not visited yet, so it is of the order of n. We multiply these two parameters to get the overall time complexity, which is in the order of 2 to the power n times n to the power 2. We go back now to the table to see how many, what is the improvement we offer. 2 to the power n times n to the power 2. Now we can use n until 18, until 15, 16, 17 of this order instead of maximum 11. So as we have seen, this allows us to solve up to n approximately 16, because it will give us, it will be of the order of 17 million operations. Of course, this is the worst case. We can hope for a better, but this is the approximation. So this is a small improvement, but this kind of solution is the best solution. We will see now in detail. If you are asked for an exact solution, if you are asked for a number of ways, if you are asked of the ways, of the different ways you can see. If n is very large, larger than 16, larger than 18, there is no exact solutions, and you will have to refer to non-exact approaches. So how to solve one state? Consider an example, detailed example. This will help us to understand how we will proceed. Consider that we have 6 cities, and you will always start by city at index 0, then you will have 5 left cities to visit, and you will consider that the first city is a default start, and you will begin by calling TSP 0, because 0 is the current city to start with, and all the 5 other cities are not visited yet, so the 5 bits are set to 1 all. And here remark, we are not using 6 bits, we are using 5 bits, because always we will start by visiting the first default city. So all the 5 cities are available, they are not visited yet. We will represent them like this. The city 0 will not enter the bit mask, so the bit mask will be indexed from 1 to 5. We will make an offset to represent this. What is the value? The value is of this mask. How do I give this value? I cannot write 1 1 1 1 1. I will have to write mask equal 1 shifted n minus 1, 6 minus 1 here, times to the left. It will give me 1 with 5 0. I subtract one value from it. It will give me the 5 ones. So this is the value 31. So I start calling the value 31. Then let's now understand how we proceed in order to know which cities are still available in a general case. Suppose we reach a random state. I chose this random state. Suppose we are currently visiting the city 3 and the mask is now 18 to the in the decimal base, which is 1001 0 in the binary base, in the base 2. What does this mean? This means that the city 2, because we begin at index 1 now, and the city 3, 4 are visited, but the city 5 is not visited yet. So we have already visited city 0, 1, 4, and we are currently visiting 3. So this is the first parameter of the recurrence. And we still have to visit the cities 2 and 5. Okay? So the question here, because there are only 2 cities to visit, do I visit 2 then 5 or 5 then 2? Which gives me the minimum cost? Which order gives me the minimum cost? So this is the representation as I was explaining. And the TSP of 318 will have to return, if it is not set yet, if it is not memoized yet, we'll have to calculate 2 things and return the minimum between these 2 values. It will have to calculate the distance from the current city to the city that is not visited yet. The first one is 2, distance from 3 to 2, plus the recurrence over 2, with which mask? With this same mask, but we'll have to remove the city 2, so it will become 1 0 0 0 0, and we'll have to calculate also the same thing with the city 5, so distance 3 to 5 plus TSP 5, but this time with the following mask 0 0 0 1 0. Okay, so the question here, how do I get 2 and 5, and how do I calculate the mask? 2 and 5 are, we will call them V, and it will be V plus 1, in fact, because we removed the index 0 from the bit mask, so we will calculate V then add 1. And the mask is nothing else, the new mask will be nothing else but the old mask with XOR with 2 to the power V. In the case of 2, V will be equal to 1. We will be calculating distance from 3 to 1 plus 1, which is 2, and TSP over V plus 1, which is 2, with the mask XOR 1 0, which is 2 to the power 1. And this way we remove the bit 1 from the old mask. Again, the same thing will be done for 5. So how to obtain V quickly? How to obtain V quickly? We will use the least significant one always. So we will get the 2 here, then the 5 when we remove 2. So we will use the least significant one, and 2 to the power V is the least significant one, in fact. And what is V? V is, we use a built-in function, which is built-in CTZ, 2 to the power V plus 1. What does this function return? Built-in CTZ, you give it an unassigned integer x, and it will return the number of trailing 0 bits in X. So it will return for you how many zeros are before X. So starting at least significant bit position, you start from the least significant bit position, it will return how many zeros there is. So V will be the number of zeros plus 1. The new mask will be the old mask with XOR operation with 2 to the power V. So we will begin from right to left, and we will find V equal 2, and then we have to find V equal 5. If we apply over this same mask the function least significant one, we will not get 5 because we will always get 2. So we will have to remove the ones we find. So this is the thing. We will take a copy of the mask, and at each iteration we will subtract from it the 2 to the power V in order to get the next least significant one. Example of the of 2 to the power V and V using these 3 lines of code. Suppose the mask is 10000, so 2 to the power V will be itself, okay, and V will be 0000. So we have 4 zeros and we will add 1. If this is the mask 01100, which is the value 12, we will have 2 to the power V 4 because the least significant one is at the third from the right, so it is 1 here, and V will be 2 zeros plus 1 will be 3. A last example, if we have, for example, least significant bit at the first position, so 2 to the power V will be 1, and V will be also 1. This was the explanation, and let us see an example. So as an application of the traveling salesman problem, the UVA 10496, which is called collecting beepers, in which we have a robot that have to collect the beepers, and so it must go and make the least cost. And the beepers are on positions, and the robot can only move up, down, left, right, and not in a random or diagonal way. This is to calculate the distances between the different beepers. And so this is a direct application of the problem, and we will proceed by using this dynamic programming solution. So we will have a memoization table. They said up to 10 beepers, so just like the cities, up to 10 cities. So with the robot itself, it will go from position 0 until position 10. And the second parameter is the mask. So the mask will be all available, not counting the robot itself, so 10 ones, until nothing available, we have 10 zeros. Of course, we will have to fill the distance matrix first. So the distance will be filled as follows. For a random entry line I, column j, the distance is xi minus xj in absolute value plus yi minus yj in absolute value, and this is called the Manhattan distance, okay, because you cannot move in a random way, you have to move along the 4 directions only. And then these distances will be copied, the first column in these distances from any line to the column 0, we will be using it in the base case. So anything when the mask is 0 will be the distance from this element to the robot 0. Okay, so this we will start calling the green the green case, so we will start calling 0 plus full mask plus the value, the full mask, okay? And then the base case is the following, is the pink, where mask is equal 0, none available or visited list, and we will be filling, in the filling order is random upon need. So whenever we need an element in this matrix, we will be filling it. So for a random case, I just copied what I explained before. It will be the minimum from distance from I to V plus dp or TSP or whatever the recursion function is called, V, and the new mask for every available V. And this is the code. It is now, it can be understood. Here you have the least significant one, and here you have the main, and you start, the answer is in GP0, 1 shifted to the left and -1 times -1. I have already explained this. Of course, before I have to initialize with dummy values, which here will be equal to -1. Negative values are dummy values in this case. Before that, also, I will have to fill the distance matrix using the formula we just explained. So this is how we prepare. And then the memo table is of max n times how many cases. It is the same number, 2 to the power n, which is 1 shifted max n minus 1 times. Okay, I have my memo table ready, my distance table ready, and I begin the iteration, I begin the recursion, and I have at each recursion the state u and mask. If the mask is 0, I will return the base case, else I will link the answer, the local reference, with memo u mask, and then if it is not -1, if it is not -1, that it is already memoized, I return it. This is a classical procedure as usual. Else I will initialize this to 2 giga, for example, a very big number, because I will be searching for the minimum. So I don't have to leave it, I have to not leave it equal to -1. And then I will copy the mask. I also explained why do I copy the mask, in order to take all the V's. And then 2 to the power V is the least significant one. V is the built-in CTZ of 2 to the power V plus 1. And then the answer is the minimum between the answer until now and the distance of UV plus the dp of V and the new mask, which is XOR with the 2 to the power V. And finally, I will return the answer. Let's see a demo. In fact, let's see 2 demos. Well, we will only see one case, not many test cases. I modified a little bit the solution so it can trace the recursive calls from one to another, one state to another, and to show you the overlapping problems. Here we have the positions, the maximum positions, the positions of the first robot, and then we have 4 beepers and the coordinates of these 4 beepers. So this is only one case. Let us run this tracing example to examine this case. So this is the tracing example. Of course, we first call dp015, which is 4 ones, okay, which is 4 ones. In order to calculate this, we will have to calculate the four cities or the 4 beepers are already available at the first call. So we will calculate the minimum between all these values from let's make a space here. Let's close this file. So this is the minimum between if we begin by 1, by 2, by 3, and by 4. In order to calculate this is backtracking. The display is backtracking because we display at the end of the calculation. So before this case, we calculated from 4 to 15 XOR 8, which is 4 to 7. So in order to calculate DP 4 to 7, we had to calculate DP 1 to 6, DP 2 to 5, DP 3 to 3. In order to calculate this DP 3 to 3, we had to calculate DP 1 to 2, DP 2 to 1. It means B per 1 and the mask equal 2, and B per 2 and the mask equal 1. However, these were already calculated because this is an overlapping situation, because this situation has already been encountered. And you can see in this way how many times, using only 4 beepers, so that the number of cities is very small, how many times you can see in the tracing overlap computed before. Overlap computed before, this will be very recurrent because, as you can see, the mask cannot take many values. You have to remove one or to set a bit to 0 or 1. So you will be, of course, returning to the same state more frequently. So this was the first demo, is the collecting beeper solution, which was seen already in the slides. So this is the exact solution we have saw in the slides. And we will get the data from the online judge. We will paste it and we will generate the requested data. And here we can compare, and of course we will get the same output, which will be identical. So this was all about the traveling salesman problem. At the end of this section, we present the table 3.4 from the textbook, which summarizes the 6 classical TP problems studied and what's the information for each one. When deranged sum query, its state, the space, the transition, and the time complexity for each state. That would be range sum query, what state, what space, what time complexity, what overall complexity, what is the transition, the longest increasing subsequence, the knapsacks, the coin change, and finally the TSP. Next, we will see two non-classical examples, which are the how do you add and the cutting stick problems.